All right, if you watched the last two videos, then you probably recognize that the template for this is very similar to the last two. Again, we're just going to be looking at another aspect of pendulums and oscillating springs. But this time we're going to look at a specific formula given for each one to determine the period, how long it takes for one complete cycle. So for a pendulum going back and forth, it is important for us to think about what variables could affect it. One variable that would affect it would be the length of the string. If the length of the string is very, very short, then the pendulum doesn't have to move very far. It's only moving a small amount back and forth, which means it doesn't take that long to do it. The other thing for us to think about that has a big effect on this is the acceleration or the strength of the gravitational field. If you're on something like Jupiter, that pendulum's really going to be yanked on. So it's going to have to go back and forth really, really quickly. And even on its way up, it's going to slow down super quickly. So we would have a really fast period. Whereas if you're on the moon and you did something like this, it would just take its time. It's not going to accelerate very fast on its way down. And then after it gets past that equilibrium position, it's going to take a while for it to slow down on its way back up. So the period of a pendulum is based off of the length and the strength of the gravitational field. But one thing that it's not based off of is it is not based off of the mass. And we kind of know that because we've seen in several different problems that the mass would cancel on this kind of thing. Because mass would increase right here, a greater mass would increase the gravitational potential energy. And it would increase the gravitational force that's pulling it down and accelerating it. But mass also increases the resistance to forces, the inertia. So even though the force is increasing, the resistance is also increasing. The mass cancels, as we've seen happen again and again. So mass has no effect on the period. It does affect the amounts of energy and stuff, but it doesn't affect the period. So when it comes time to figure out the formula for the, oops, that should be a P, period of a pendulum, P or T for period, P for pendulum, also, obviously. So the period of a pendulum is 2 pi times the square root of the length. As the length increases, the period increases, over G. As the strength of the gravitational field increases, it's getting yanked on harder, so it would go faster. So make sure that you're watching these relationships. If L goes up, then the period of the pendulum goes up by a square rooted amount. So if this went up by 2, this would go up by the square root of 2. If this went up by 4, this would go up by the square root of 4, that kind of thing. Conversely, if the gravitational field strength increases or the acceleration due to gravity, then the period would actually decrease by 1 over the square root of whatever it is. So if the gravitational field strength went up by 2, our period would actually be 1 over the square root of 2 decreased. The big memo that I want you guys to get is that mass doesn't matter. So mass plays no part in a period's, the pendulum of a period. The other thing that doesn't really make a big difference is the angle. Oops. The angle mostly doesn't matter. And what I mean by mostly doesn't matter is that as long as you keep it below 10 degrees, it's not going to play a huge role. So that's a simplification that we're making. That is why this is simple harmonic motion, because we're only looking at pendulums that are going between 10 degrees if we're looking at the period. If we're talking about forces and energy, who cares? We don't care what the angle is. But for this particular equation, it has to be at something below 10 degrees for this to really work well. It can even kind of go up to 15 degrees with an acceptable error, but you don't want to go much higher than that. So definitely be watching that in your experiments this week. Keep your angles low. You can kind of eyeball it. 10 degrees is about, like, if this is upright, 10 degrees is about here. So just don't pull it too far, and you'll get results that work out just fine. All right, now for a spring, whether it's horizontal or vertical doesn't make a difference. There's still only two things that impact it. The first thing that's going to make a difference is M. In this case, mass does matter because it's not affecting the force acting on it horizontally. It's only affecting how much it resists the changes in motion. So as M increases, it makes sense that this thing would move slower because we have the same spring, but it's just not going to be able to accelerate as fast. So our average velocities are lower and it's just not moving quite as much. In the vertical case, force of gravity does play in here, but because spring force is still there and it still has nothing to do with mass, mass still doesn't cancel, and it plays the exact same role in the vertical case as it does in the horizontal. The other variable that affects this is K, the spring constant. The stronger the spring, the more force we're going to get, the more acceleration we're going to get, the faster we're going to get things done. So the relationship is going to look really similar here. Our spring period is 2 pi times the square root, but this time as mass increases, it resists it, so that slows it down, so mass goes on the top. But as the spring constant goes up, it's able to yank it around faster, which means it would a bigger spring constant would be a lower period. So the spring constant kind of plays the same role as the acceleration due to gravity, and the mass and the length play similar roles. In this one, there's again something that we want to emphasize doesn't matter. In this one, it's the displacement. The displacement cancels. So while pulling it back gives us more force, it also gives us more distance to travel. So the more distance would kind of lead us to assume that the period would be longer, but the more force would lead us to assume that the period would be shorter. But because it's a little bit of both, mathematically the displacement cancels. So cancels. So make sure you're paying attention to that. That's usually the kind of questions that they're going to ask. So you can say, all right, we pulled this back twice as far. How does that affect the period? And it doesn't. It affects the energy. It affects the speed in the middle, but it doesn't affect the period. And then the big thing is a lot of the time you're going to have questions that compare pendulums and springs. They're going to say, all right, we set these both up. They have the exact same period. We double the mass of both. What does it do? It will affect the period of the spring, but it will have no effect on the period of the pendulum. So again, same thing that I kind of did off to the side here. You want to make sure that you know if mass increases, what happens to the period of the spring, and as the spring constant increases, what happens to the period of the spring. It follows the same pattern over there, but I want you guys to kind of think through it on your own. So there's everything that you should hopefully need to know on the simple harmonic motion period formulas.